Hello, my name is Kevin Cavell, and I'm a product manager working for Agilent Technologies. Today I'm going to demonstrate using one of our new higher power DC power modules in our DC power analyzer mainframe. And in order to show you that, we're going to be testing a radio transceiver that I have here today. And we're going to be doing 3 measurements. We'll do a off mode current measurement, a standby current measurement, and a transmit current measurement. And one of the benefits of the new N6764A module that we have installed in the DC power analyzer mainframe is that it has 2 built-in current measurement ranges, a high range and a low range, so we can accurately measure the high level currents as well as the low level currents. So I've already set up the DC power analyzer mainframe and the module installed to be set at 14.4 volts and 20 amps. The particular module that's installed can source up to 60 volts and 20 amps with a total output power of 300 watts. Today we'll come a little close to that, you'll see. So the output right now is off, so if I just turn the output on, we'll see we're sourcing the 14.4 volts to the radio, and we're seeing about 3.85 milliamps of current being drawn by the device, even though you can see it's not powered on at all. So this is the off mode or leakage current that the device will draw constantly, whether it's connected to a battery or not. So if it is connected to battery, you want to be careful, because if you leave this off for too long, you will actually drain that battery all the way to the end. So I mentioned that this particular module has 2 built-in measurement ranges. In order to get this very accurate, almost 4 milliamp measurement, we're actually in the lower measurement range. It's easy to change ranges just by going into the properties section. And right now I have it on auto. That means that the range will be chosen automatically by the module depending on the output current. But you can see the other 2 ranges are 20 amps as well as 500 milliamps. So depending on the accuracy you need, you can choose the appropriate range. I'm going to turn it back to auto because we'll be going much higher than 500 milliamps. All right, if I go back to the meter view, again we're off. We're pulling about 4 milliamps. If I turn the power on to the radio, you'll see that with the radio on, we have a steady state current of about 1.3 amps, and that equates to about 20 watts of power that we're sourcing to the radio while it's just sitting here on standby. So it's a pretty significant amount of power just to be sitting here without transmitting or receiving. If we want to measure how much current is drawn when we're transmitting, all we have to do is click the microphone here, and we can see it jumps up to about 18 amps and 260 watts. I mentioned earlier that the module can go up to 300 watts, so we're using almost all the power that can be sourced by this particular module. So it's a significant amount of power that's being drawn by the radio during transmit. So it's very important when you're testing something like this type of radio or a military radio that's going to be mounted inside of a vehicle and powered by a battery, or even military radios that are larger but powered by just a battery alone. You want to be careful about how much power is being drawn in off mode, in standby mode, and during transmit to make sure you get the most use out of that. So it's very easy to make these measurements with the new N6764A module that we're using today. Another thing I'd like to show you when testing a device that will be running off of vehicle's power is an alternator whine test. What alternator whine is, when the alternator is spinning, it could potentially create a waveform that will be injected into the devices that are being powered off of the electrical bus. And that waveform can cause problems with the device, or it could bleed through the system and end up coming out of the speaker. We can simulate that test using this system. The N6700 modules all have the ability to create waveforms. Even though they're power supplies, they can be used to create waveforms. The N6764 is one of our faster modules, so it can create fast waveforms in the kilohertz range. So we'll create that now very easily using the DC power analyzer. We can go into the arbitrary waveform setup screen. You can see we have a choice of a few different waveforms. We're going to use a sine wave this time. If we go into the properties, you can see I've already created my sine wave with a peak-to-peak voltage of a 1/2 volt, so a 1/4 volt per side. The DC voltage will be 14.4 volts, so we're going to be riding that sine wave on top of the 14.4, and the frequency of the waveform will be 1,000 hertz or 1 kilohertz. In order to start this waveform and inject it into the radio, all we have to do is hit the ARB run stop key, and all of a sudden you can actually hear the kilohertz sine wave coming through the speaker, and I can start and stop it. So another interesting thing that we can do with this system, especially the N6764 modules, they have dual digitizers that are constantly measuring the voltage and the current of the output. And we can view the information, or the measurements that are being made by those digitizers in our scope view. So if we wanted to see what the sine wave we created looks like, we can set up the scope. It's very similar to an oscilloscope. We set the run stop key, and if I hit the ARB run stop key again, we can actually see the sine wave that we created. So I can stop it, start it up again, and you can hear the sine wave. If I hit the scope view key one more time, that actually brings up the markers, and we could take some measurements if we wanted to. And if I bring the markers to the peaks of one period of the waveform, we can actually see at the bottom here, it's probably hard for you to see, but it says 980.4 hertz, which is roughly 1 kilohertz. All right. So one other interesting thing we can do using the scope view is earlier we did a standby current measurement that was 1.3 amps when we turned on the radio and just let it sit there without transmitting. Typically when you first turn on an electrical device, there's some inrush of current, and that can be very high. So we can actually measure that using the scope view here. So let's do that. We'll turn the radio off, and I'll set up to measure the current in scope view. So I just need to go in and change my trigger levels from voltage to current. So I'm changing from voltage of channel 1 to current of channel 1, and my trigger level is set to 2 amps. So if we go back to the scope view, we're all set up. We just press the run stop key. It's lit, so that means it's waiting for us. It's waiting for a trigger. And if I hit the power on, you can actually see that we captured that inrush current, that peak of current. As it shoots up, the current rushes into the device, and then it starts to settle. So you can see that we don't see it settle all the way down. So if I just change my time base, you can see it better. We can actually retake this measurement real quickly and see a more complete waveform. So there's the inrush current. If we want to know how high this peak is, again, we could turn on the markers by pressing the scope view key again, move the markers around that point, and in the corner here you can see that maximum is 5.5 amps of inrush current. So a little bit higher than the 1.3 steady state, but not too high. In some cases with certain devices you see a significant amount of inrush, but here you see about 5.5 amps. So again, it's a very easy way to make very complicated measurements. Usually you have to have a pretty sophisticated setup with an oscilloscope, a DMM, a current probe, Here we have it all in one system, and with the advanced capabilities of the different modules that you can put into the mainframe, it makes making these types of measurements very easy. Thank you.